Section 4.5 in our book, the second part, has to do with equations involving logarithms. Instead of having exponential functions where we put the logarithm into the problem, we are going to start with logs in the original problem. Also, just like there were two types of approaches to approaches for two types of problems in that first part of 4.5, depending on what we're given with our logarithm equations, we're going to have two different approaches there as well. The first situation, and we'll start off slow and steady, involves our one-to-oneness of our logarithm function. If we're told that log base b of x is equal to log base b of y, we know that can only happen if x is equal to y. So if we had something like log base 2 of x is equal to log base 2 of 3, we would conclude that that can only happen if x is equal to 3. Or if log base 4 of x plus 7 equals log base 4 of 12, then the only way that can happen is if x plus 7 is equal to 12. But knowing that log of this is equal to log of that implies that these two expressions have to be equal. So if we set them equal to each other and then solve for x, then we have our solution. Now, of course, when we're solving equations, they aren't always going to be that short and sweet. We might have something like log base 2 of x plus log base 2 of, scratch that last idea. If we start out, let's keep something small for a little bit longer. Let's say we have log base 7 of x plus 1 equals log base 7 of 2x plus 5. Then we know that can only happen. Log of this can only be equal to log of that if this is equal to that, meaning if x plus 1 is equal to 2x plus 5. Now when I solve this equation for x, I move the x's to the right, I subtract 5 from both sides, and I find out that x is equal to negative 4. Now the thing we have to keep in mind here that we didn't have to worry about with our exponential equations is the domain. If I have b to the x, I know that its domain is all real numbers. But with our logarithms, log of any base, we can only take the log of positive numbers. So if I plug in negative 4 for x, it says I have log base 7 of negative 3 equals something. And log base 7 of negative 3 can't happen. We cannot take the log of a negative number. We also cannot take the log of 0. So once we solve for x, we always have to take the number that we get for x, we have to plug it back in to our expression, and we have to make sure that we're within the domain of our functions, meaning when I plug the negative 4 in for x, I can't be asked to take the log of a negative number. So since negative 4 doesn't work, I have to mark it off the list, and anytime I mark off every number that I had on my list, then I conclude that there's actually no solution to this equation. So every time we solve for x, we need to take the x back to the beginning, plug it in every place there's an x, and make sure I'm only taking logs of positive numbers. On the next one, let's look at log base 2 of x plus 1 plus log base 2 of 4 minus x, and we know that that's equal to log base 2 of 6x. So let's say that that's the equation that we are given and that we're asked to solve this for x. Now our one-to-oneness of our log functions doesn't say anything about what we can do when we have sums or differences. So what we have to do in order to make it look like, back and forth here, to make it look like this, so we can draw the conclusion on the right, this is where we get to use our properties of logs. So I know plus goes back together as a product. And so we'll have log base 2 of the product of these two expressions equal to log base 2 of the 6x. Then I can go ahead and I can FOIL on the left. Nothing to do on the right there. And then we're back to knowing that log of this can equal log of that if and only if this equals that. Meaning I can set the stuff in parentheses equal. There's no x there. Negative x squared plus 3x plus 4 equals 6x. So we can say if log of this equals log of that, then this has to equal that. From here we can solve for x. If I have an x squared, I like to get a 0 on one side. I like to get everything else on the other, and most of the time if I can get it done, then I like to keep my x squared term positive. The easiest way to solve a quadratic equation, if possible, is to factor the polynomial. And then I can set each piece equal to 0 and solve for x. Now again, if we take these numbers and plug them back in to where we started, to those expressions, any place there's an x, we have to check and make sure those expressions are positive. Okay, 6 times negative 4, not positive. Now 4 minus a negative 4 is okay, but I get a negative 3 here, or a negative 24 over there, which means negative 4 is not a solution to my equation. It's not a number that I can use. If I take the 1 and do the same thing, plug it in all 3 places. 1 plus 1 is 2, 4 minus 1 is 3, 6 times 1 is 6. All of those are positive, which means the value x equals 1 is in my domain, and so it is my only solution for this equation. The goal is to get it set up using our properties of logs, where a sum turns into a product. If I had a minus sign, it turns into a quotient, and this is how we approach a problem when there are logs in every single term.